Well, let me tell you about Professor Cowburn. He's got research interests in nanotechnology, its application to magnetism, electronics and optics. He's a professor in Cambridge and has been for the last 10 years. Before that, he worked at CNRS in Paris, at Durham and Imperial College. And he's the founder of several startup companies and also a fellow of the Royal Society. So it's a great pleasure to introduce him today. And let me, without further ado, just hand over to Russell and he'll give us his talk today. Thank you, Russell.
Great, thanks very much, Bob, and good morning, good afternoon, good evening, wherever you are. It's very good to be part of this summer course. So this morning I'm going to speak as a physicist, increasingly a physicist with biological interests, but primarily as a physicist about randomness. And sorry, there you go. Christian theologians have wrestled with the problem of randomness for many centuries, actually. And there are two problems that come out of it for the person of faith. The first is that random processes, and by that might be the throw of a dice, or it might be some chemical bond in a reaction that may or may not break. These things are all unpredictable. That's the definition of a random process. We cannot predict in advance the particular outcome. And is that a challenge to God's omniscience? How can God know everything if the outcome of a random process isn't knowable? The second problem that has challenged Christian theologians is random processes lead to contingency. Things might happen differently depending on a particular random result. And how does that therefore challenge God's omnipotence? How can God be in control of everything if outcomes depend on unknowable processes? So theologians have talked an awful lot about this. And very simply, I'm going to say, I think a lot of these problems are dealt with by Proverbs 16:33, which says the lot is cast into the lap. That's a random process, but its every decision is from the Lord. But in fact, this isn't really what I'm going to talk about today. I wanted to put this up because I think as soon as people start talking about randomness from a theological perspective, people assume that this is what they're going to talk about. But actually it's not. I want to talk about something slightly different. And I'd like us to just play fantasy creation and just try to imagine how we think nature should be arranged. It's really important to Christians, it's really important to people of a variety of faiths, because certainly Christians have the theological view that the physical processes at work in the creation reflect the nature of the creator who is behind those. So, for example, in the biblical book of Revelation, it says, "You are worthy, our Lord and God, to receive glory and honor and power, for you created all things, and by your will they were created and have their being." So the reason that God is worthy to be praised is because of the things that he has made. This very strong link between God and God the Creator and his creation. Similarly, the Psalm 19, that famous psalm for scientists, the heavens declare the glory of God, the skies proclaim the work of his hands. So here the idea is that God's creation speaks about the one who made it. And so it's really important that we understand all of the elements of creation and how to interpret those, in what way they reflect God's character. And this is where the problem starts with random processes. So here, for example, is a graphic showing part of a human brain. And it's this huge tangle of neurons and synapses. And from the outside, if you were to look at this, I think the words that would come to mind are not particularly complimentary. They're words like messy, disorganized, uncontrolled, random, and maybe even badly designed. Certainly, if I put my engineer's hat on and I go in there, I immediately say, well, we could do with a few cable ties and a little bit of labeling of the connections, and a circuit diagram wouldn't come amiss. And yet those things we never find in natural structures like the human brain. Compare that with what an engineer or a scientist would consider something properly built. This is part of a microprocessor. So this is the sort of thing that runs your PC or your mobile phone. And immediately the order and the precision leap out at us. It's very predictable. There's a high degree of perfection. And certainly by human standards, we would say that this is well designed. And if we look at the way engineers and scientists go about solving problems, and we compare those with, for example, evolution, the comparison is quite striking. So any student of engineering is always taught the engineering design loop. It's this systematic process of how you go about designing and building things. So you start at the top right, identify the need, you research the problem, you develop possible solutions, you select, you construct, you test, you communicate, and then you redesign. And you go around this loop. And every time you go around the loop, your engineering solution gets better. And this process is characterized by a high degree of structure. It's very ordered and it's very efficient. And this is how everything from microprocessors to jumbo jets are built. Compare that with what we call the phylogenetic tree of life. This is like the family tree of all of living creation. So the big three divisions of bacteria, archaea, and eukarya. And you've got this enormous complexity of things that most of us didn't even know existed. And if we say, well, where are we in this? We are somewhere around here between slime molds and fungi. And people may be tempted to say, well, isn't this wasteful? Isn't this disordered? All this randomness, it seems to lack direction. There is much talk about evolution by natural selection. I'm sure that's something that we will talk about a lot this week. But as a simple physicist, let me boil it down to what's at the heart of evolution by natural selection. It's a two-step process, effectively. You have parents. Those parents have offspring. But in the transmission of genetic information from the parents to the child, there is the introduction of some randomness, some random mutations. The child is not a genetic clone of the parents. There are always a small number of differences. And it's those differences which actually drive evolution. That child is then exposed to the environment that it happens to live in, with all of its stresses and all of its need to survive. And depending on how well those random mutations have adapted the child for its environment, will determine whether it survives or not, or at least survives long enough to have children of its own and become parents, and we go round and round the loop. And out of that iterative process of going round and round the loop comes a well-adapted population. In other words, a population which lives well in the particular environmental niche that it finds itself. And again, this is the problem for many people of faith, that at the heart of this, what I personally consider to be a wonderful process, a wonderful engine for adapting to a population. But at the heart of this lies this process of random mutations. And how does that fit with our theology of God? And so if we just sum up the problem to many people is that they are uncomfortable with the fact that evolution by nature but by natural selection is built on randomness. I speak to a lot of church groups, a lot of Christian groups, and every time I speak to them, especially during the Q&A, you can just sense this unease about the way that random processes are built in to the evolutionary process. And even if we, as I do, accept the idea of theistic evolution, that is to say that the scientific process that we know as evolution by natural selection is actually God at work, that is God's chosen mechanism for filling the world with life. even if we accept that, it still leaves the question, why would God choose to use such an apparently inefficient and maybe even unthinking method as randomness to drive his creative purpose? Doesn't the random nature of evolution just make God look like a bad engineer? Is the use of randomness in creation worthy of God? Does it sufficiently reflect his character? Could I even ask, are Christians embarrassed by God's use of randomness and wish he'd used more perfect and ordered methods in his creation? Certainly when I speak to Christian groups, that is the sense that I get from people. And in short, aren't order and perfection, instead of randomness, just better reflections of the character of God? And so they should be at the heart of his creation and not the randomness that there appears to be. So this is the problem. This is really what I've been thinking about and what I'd like to hopefully give you an answer to. So my aim for the rest of this talk is very simple. I'd like to convince you that disorder and randomness are not inferior to perfection and order. And I want to do that by showing you that disorder and randomness are actually essential for physics. I want to show you that disorder and randomness are essential for life. And I want to show you that actually, far from being the marks of a sloppy engineer, disorder and randomness are already frequently used by the best engineers. So let's look briefly at disorder and randomness and how important they are in physics. And I'm going to do this just by taking a few examples, things that I know about, things that I've used myself. So here's something from my world of nanotechnology. Those of us in the nanotechnology spend a lot of our time finding ways of building nanostructures. So a nanostructure is a structure that's made up from single atoms. And obviously it's very difficult to control materials with atomic level precision. And just to give you a flavor, this is something that's been built in my lab over the last few years. It's essentially a club sandwich, lots of different layers of different materials. We've got a whole range of different elements in there: cobalt, iron, boron, platinum, ruthenium. And they're all very thin. Each one of those is less than 1 nanometer thick. And typically an atom is about 1/10 of a nanometer. So each of these layers in the club sandwich is only a few atoms thick. And ideally, this is what we would like to create at the interfaces. As we go from one material, in this case, say platinum, into another material, say ruthenium, we'd like there to be a continuous atomic plane of platinum, and then we'd like that to immediately transition perfectly cleanly into an atomic plane of ruthenium. And indeed, we need that. If we can't build that almost seamless transition from one type of atom to another, then we can't do our work. One of the problems with building with atoms is that they tend to adopt a very high level of regularity. So I'm sure those of you who've studied science at school will remember that atoms form lattices, and those lattices are very perfect. The spacing between the atoms is exactly right, and the layout of the lattice is very precise. But what you may also remember is that sometimes things go wrong, and sometimes you end up with a missing atom. And when that happens, the rest of that atomic plane collapses, and you end up with what we call a defect. And this always happens. It can't be avoided. And the problem for the nanotechnologist is that when that random missing atom happens to hit, you get a defect that then propagates through the rest of your structure and ruins it. So you can see there the slip plane of atoms. And it's a bit like the princess and the pea. You remember the story of the princess and the pea? The pea is under the bottom mattress, but it causes a bulge in the layers above. And the princess is so sensitive, by the time she lies on top of the stack of mattresses, she can still feel the bulge that's worked its way up through the layers of mattresses. And that's exactly what my atomic planes are like. One slipped atom at the bottom of the club sandwich ruins every layer going upwards. And here's the fun bit. The solution is actually to introduce randomness. The way we do that is by using the metal tantalum and by making it very thin. And when you make tantalum thin, it loses all of its order and it becomes disordered, or amorphous, as we call it. There's no longer any regular atomic lattice. And the beauty of that is that if you have a missing atom from a random collection, nobody notices. It doesn't propagate up through the stack. And if you look at this little cartoon of atoms, you see the bottom, in the bottom right here, there's a missing atom. That one there has gone missing. But by the time you get to the top, the order and the position of the atoms is almost exactly the same as if that atom weren't missing. And we talk about the random tantalum atoms as healing the structure. They absorb the defect and stop it from propagating. So without that amorphous layer, without a layer that lacks order, it would be impossible to build highly ordered nanostructures. We have this surprise that the way you achieve perfection is by introducing imperfection and randomness. And this is true across a lot of material science. Materials with randomly ordered atoms often have the property of healing defects, whereas materials that have too much precision, materials with precisely ordered atoms, do not have that healing capability. So that's one example from material science. Let me show you something else from physics, quantum mechanics. And quantum mechanics is the heart of all of modern physics. It's a little bit complicated, but I'm going to try to make it simple. So at the heart of quantum mechanics is we think about the states that things are in. So for example, a given particle could be in two states, in state A or in state B. In this case, I've represented state A by an upward arrow and by state B by a downward arrow. And there are three possibilities for how we could find that particle. It could be purely in state A, it could be purely in state B, or it could be in what we would call a mixture of states A and states B. And it's the mixture of states where quantum mechanics differs from our more intuitive view of the world, our classical view of the world. Let me give you an example. If you imagine mixing colored light. So if I choose, if I take red, blue, and green light and mix them together, in our world, a classical world, that mixture of those three things gives you white light. At a quantum level, though, that's not how you combine things. If I have a mixture of state A and a mixture of state B, when I observe the particle, what I actually see is a random choice being made between A or B. I don't actually see the mixture. I see a random selection between the two things that make up the mixture. So it will be equivalent in colored light of saying, if I mix red, blue, and green light together, then 1/3 of the time that I look at it, I see pure red. 1/3 of the time that I look at it, I see pure blue. And 1/3 of the time I look at it, I see pure green. So a very different way of understanding a mixture. And so randomness is at the heart of quantum mechanics. And quantum mechanics is at the heart of all of physics. The way we understand atoms and electrons and everything smaller than that is purely by quantum mechanics. And it was this idea that we have such randomness at the heart of everything that really bothered Albert Einstein. You'll be aware of his famous quotation, "I cannot believe God plays dice with the universe." But it seems that's indeed what he does. And yet, the surprise here is that quantum mechanics, despite having randomness at its heart, is also the source of the most pure perfection that we know of. So a simple example, if you go into the street and you look at an old style street lamp, I know most of them are LEDs now, but if you can find some of the old style sodium lamps, the ones with the yellow glow, the wavelength of that yellow glow is really precisely defined. It doesn't have any of the variation or the engineering tolerance that you might normally expect to find in an engineered object like a light bulb. it's always 589.3 nanometers. The color of that light is precise. And it's because the yellow color in a street lamp comes directly out of quantum mechanics. And so out of the randomness of quantum mechanics comes precisely defined energy levels and this new level of precision. So once again, we have this dichotomy of you need randomness in some places in order to achieve perfection elsewhere. Here's another example from physics. I love this. This is what we call Monte Carlo simulations. And a lot of physicists spend their days worrying about how to solve equations like this. So some function has 19 or 20 or even more variables, and there is one set of those 19 or 20 numbers for which that function equals 0. And the problem is how to find that one particular set of variables that gives you the right answer. It's a really hard problem. Now you might think, well, that's a pretty pointless thing to spend your time doing. But one of the famous applications of this is called the traveling salesman problem. And actually, this is directly applicable to things like Amazon deliveries and Uber and all the things that we think of as modern, making up modern life. And the traveling salesman problem is you have a salesman who has to visit a number of customers in different cities, and he wants to find the most efficient route to travel between those cities to minimize the total distance that has to be traveled. And the way you solve that problem is by solving an equation just like this. And it's ferociously difficult to do, even with the best of today's computers. And how do physicists actually do it? They do it through randomness. What they do is they set up effectively a casino game. That's why it's called the Monte Carlo approach. And they try random approaches. They say, well, let's try going to this city first and then that city next. How efficient is that? And they keep doing these random trials, and eventually they find the best of a large number of possibilities. So even physicists with their computers and their assumed precision actually use those computers sometimes to roll virtual dice in order to solve difficult mathematical problems. And there's a related technique which gets even closer to evolution by natural selection called genetic algorithms. So if you travel out into rural Oxfordshire, you will stumble across this enormous building. It's called Diamond, and it's one of the world's brightest sources of X-rays. And a lot of physicists, myself included, use that source of X-rays in order to study materials on the atomic scale. And quite often these materials look like this. It's a bit like our club sandwich that I showed you earlier. You've got different layers, and you want to be able to analyze them layer by layer. And what you do is you scatter X-rays off them at different angles, and you measure the strength of the X-ray reflection. And then you build a model in a computer. You say, well, let's assume that layer 1 is this thick, and layer 2 is this thick, and layer 3 is this thick. And you simulate it. And you say, well, the simulation of that, does that match the experimental data well or badly? And you keep on refining your guess until you find a very good match. And one of the ways of actually doing that process is by setting up a game of life inside the computer, where the description of the structure is effectively your DNA. And the quality of the match to the experimental data is a measure of how well adapted that species is for its environment. And you let the solutions, in a mathematical sense, have children, and you combine their genes, and you run all the same processes with all the same randomness that you have in real life. You run these numerically, and you find that you very quickly converge on a solution that is the best fit to experimental data. So again, the way you get accurate, precise measurements out of things like Diamond is by introducing a random algorithm in the data fitting. And let me just say, in passing, about the maths of randomness. Sometimes people are surprised by that and say, well, how can you do maths with something random? How could I do maths for a game of heads and tails? And the answer is, well, actually very, very easily. Although you can't say anything about the next toss of a coin, there are lots of laws of statistics that govern large numbers of random events. So things like law of statistical regularity, central limit theorem, ergodic hypothesis. These are all mathematical laws which apply to populations of random things. So we shouldn't think that randomness is uncontrolled and can't be handled by science. We've got lots of laws that work very well, as long as we look at the statistical population and not just one particular example. Okay, that's quite enough about physics. Let me more briefly talk a little bit about life, because that is something that's very dear to all of our hearts. So I'm a really bad chemist. I wish I were a better chemist, but I'm a terrible chemist. But there is one law of chemistry which I've come over the years to absolutely love, and it's called Arrhenius's equation. And this is it here up in the top left. P equals e to the minus delta E over KT, where K is Boltzmann's constant, T is temperature, and E, capital E, is an energy barrier. And the way you use the Arrhenius equation is if you have a simple chemical equation, so two different types of atom, A and B, and they may combine to form a compound AB, or that compound AB may fall apart to leave the individual atoms A and B. And the way a chemist thinks about this is with an energy profile. So we've got two valleys, low energy points, with an energy hill or a maximum between those two. And you may know that a lot of physical processes are driven by the desire to minimize their energy. But in practice, things aren't very well defined energetically. There's always randomness in the energy of something. And it's that randomness is what we call temperature. From a physicist's point of view, if something is hot, it means it actually has more randomness in its energy. And if it's cold, it means the energy is more predictable. So if I've got a chemical reaction, A plus B gives me AB, then the way I think about that is the energy of the system is bouncing around, first in the separated A plus B state, and then at some point that random fluctuation of energy is enough for it to jump out of its energy well, cross over this barrier, and end up in the other well. So this is how physicists and chemists think about chemical reactions. And the thing that really determines whether a chemical reaction will happen is the probability of this random fluctuation being strong enough to jump over the barrier and go from the unreacted state to the reacted state, or vice versa. And there's some wonderful, wonderful maths in the Arrhenius equation. Really simple maths, but still very wonderful. If I were to say, let's assume that barrier, the barrier separating these two states, is half an electron volt high. The electron volt is the unit that we use to measure the height of that barrier. If it were half an electron volt high, how long would it take at room temperature for a particle to cross the barrier, to have enough fluctuations to jump over? And if you put the numbers into the Arrhenius equation, the answer is about half a second. So in reality, that means the reaction will happen within about half a second. So that is a pretty fast reaction. Here's the magic. Let me change the height of that barrier slightly. I'm going to go from half an electron volt to 1 electron volt. How long does it take the reaction to happen now? You might say, well, it's twice the height of the barrier, so it'll take twice as long, so maybe 1 second. But sadly, you would be wrong. It will take 7.5 years. And this is because of this exponential part of the equation. And this is really important because it means that random fluctuations in energy allow chemical reactions to be precisely selected according to their energy barrier. It means that a half EV barrier will happen almost immediately, and a 1 EV barrier will almost never happen. And that's how nature controls which things react, which reactions occur, is by fine-tuning this barrier so that random fluctuations of energy may or may not pass over it. And it's a remarkably sensitive filter. Now let's just play, again, fantasy creation. Imagine what chemistry and life would be like if we didn't have random fluctuations in energy, if energy was precisely defined as maybe we think it should be. Well, for a start, most chemical reactions would not happen. It means you'd be stuck in the bottom of one of these energy barriers forever, and you would never be able to go from one state to the next. So we wouldn't have chemistry. We wouldn't be able to select different reactions according to their energy. So it means all reactions would have the same probability of happening. That means, for example, in DNA, the selective base pair binding between A and T and G and C, which drives DNA and drives all of genetics of life, wouldn't be possible. Enzymes, that really important biological catalyst, they work by controlling the height of those energy barriers and changing the probability that fluctuations will get through them. We'd be without enzymes. So imagine a world without DNA, without chemical reactions, without enzymes. That's a universe with no life. That is a cold and sterile universe. So life is only possible because of the random fluctuations in energy that are at the heart of all of chemistry. And then finally, let me just say a word about disorder and randomness being used already by the best engineers. So as Bob said, I'm from the Cavendish Laboratory, that's the University of Cambridge's physics department. And if in 1874 you went to the Cavendish in Cambridge, then you would see this picture on the left. So it's a stone building. Just as a word in passing, this building is actually really significant in the history of science and religion, because although you can't see it here because the door is open, if the door were closed, what you would see written on there in Latin are the words, "Great are the works of the Lord." And it's because James Clerk Maxwell, the founder of electromagnetism, who founded the lab and was the first professor there, he was a Christian. And he recognized that the work that went on inside that physics lab was the study of the works of the Lord. And he wanted it written on the door so that everybody would remember that on their way in. So that's what the building was like in 1874. Last year, we started to build a new Cavendish laboratory. And this is a picture from the building site. So it's a very different structure. And probably the biggest difference between those structures is the 1874 building was made of stone, whereas the 2020 building will be made of steel. And so how do engineers make really strong buildings using steel? And the answer is through the use of disorder and randomness. If I were to take one of my microscopes and zoom in on one of those steel struts that make the superstructure for any building, I would see iron atoms, and I would see a very regular arrangement of them. At least it would be regular if I look over a short distance. But if I look over anything more than just a few atoms, what I would actually see is this. I would see defects, we call them grain boundaries. And these are random places where the atomic arrangement changes from one orientation of a lattice to another orientation. So it's perfectly ordered within each grain, but where those different grains meet, it's completely disordered and random. And the surprising thing is that it's those grain boundaries are what are responsible for the strength of steel. If we didn't have them, if all of the atoms were arranged in a perfectly regular fashion in steel, then if somebody chipped the edge of one of the pillars, the crack would propagate all the way through and the entire thing would shatter. It would feel as if it was made of glass. In fact, it would be brittle. With building steel, with strong steel, what happens is you have a little crack, it begins to propagate, and it propagates as far as one of these random boundaries, one of these random defects, and it stops. And it protects the rest of the structure from damage. So we need the randomness in order to create the strength in a building. Just a very silly, simple example. Which do you think is the better biscuit? Do you prefer a Carr's table water biscuit, or do you prefer what I used to call as a child squash fly built biscuits, the Garibaldi biscuits? Apologies to those of you from different cultures who don't share the delights of these two very British snacks. But what I can tell you from long experience is the water biscuits are a real mess to eat, because you take one bite and the whole thing collapses and it makes a mess down your front. Whereas the Garibaldi biscuit, you take a bite and it doesn't make a mess because the crack doesn't propagate. And it's exactly the same process. you have the random distribution of these currents in the Garibaldi biscuit that stops the crack from propagating and makes it tough. Whereas in the water biscuit, it's pure, it's more perfect in a sense. It's only one type of biscuit, but it becomes brittle and not very strong as a result. So there's a little aid memoir to why randomness is a useful thing in materials. And we could go on. So in engineering, for example, nuclear power, nuclear reactors, they are at their very heart a truly random process. Uranium-235 atom absorbs a neutron, becomes unstable, uranium-236, and then at a precisely random time later, splits into two smaller atoms and releases energy as it does so. And you can describe the mathematics of this process. You can write an equation down, but it's an equation of statistics. And it's, again, one of these laws of maths which describes random events. And I think it's fair to say that radioactive decay is probably the most random process known to humans. And yet engineers use that at the heart of what are probably the most carefully and precisely defined engineered objects, namely nuclear reactors. So again, randomness and precision hand in hand. One final example, and then I'm going to stop. And this might be something that you've never given more than 10 seconds thought to in your life, but let me encourage you to think more and to appreciate the beauty of an electricity transformer. You sometimes see them at the end of streets or on industrial sites, but they are really what allows us to transport energy around the country. And if we didn't have transformers, we would all have to have our personal generators at home. And it would make electricity far less ubiquitous. It would be a very specialized sort of thing instead of everybody having access to electricity. The world would look like the 18th century, essentially, without transformers. And the big problem with a transformer is what are called eddy currents. There's a strong magnetic field inside a transformer, and that causes little loops of electrical current inside the magnetic materials, and those get hot and generate waste heat. And if you don't control those, you find that you can't transmit your energy from one end of the country to the other. What's the answer? It's randomness. Engineers and material scientists make something called electrical steel, which is essentially normal steel, but with silicon atoms placed randomly throughout it. And it's the random position of those silicon atoms breaks the current loops, stops them from forming, and reduces the amount of waste heat dramatically. So next time you switch on a light, think of the electricity transformer that makes it possible, and think about how engineers intentionally introduce randomly placed atoms to make it efficient and not overheat. So as a final thought, let me encourage us to redefine our word associations of random processes. We started this lecture with the idea that anything random was messy, disorganized, uncontrolled, and possibly badly designed and wasteful, lacking direction. Instead, let me encourage you to throw away those ideas and replace them instead with a different set of words. Personally, I think the right words to define or to be associated with random processes are words more like self-healing. We've seen how random atoms can heal defects. Adaptable. It's the random nature of evolution which allows it to adapt a species to its environment. Understandable, it's not uncontrolled. There are very strong mathematical laws of randomness. And those laws make random process predictable, at least when viewed correctly, when viewed as an ensemble and not as an individual event. Possessing hidden order. Rich, useful. We've talked about nuclear power and building buildings and transformers. Emergent. Emergent is the idea that although you can't see any order on an individual level, if you zoom out and look at the whole population, you see something come out of the whole that isn't visible for the individual. And that is very much the case with random processes. Creative. There are things we can do that just wouldn't be possible without the use of randomness. And with a theological hat on, maybe even merciful. I find a great mercy in the physical process of evolution by natural selection, the fact that it allows creatures to adapt to often hostile environments and make those environments places where they can thrive. And randomness is at the heart of that ability to adapt, and therefore it's a merciful thing in our creation. Okay, so I'm done. Let me just conclude. So at first sight, nature can be thought to be disorganized and inefficient, and that in contrast, human engineering appears to be much more ordered and better designed, relying on deterministic and planned processes instead of the random ones and the disorder that nature appears to use. And some have a theological problem with that. Some think that God ought to be more like a good engineer and be more about order and planning than about randomness and disorder. And I would challenge that. I would say that randomness and disorder are actually some of the most powerful tools in physics, allowing precision to come out from them, allowing precise nanostructures to be created, allowing quantum mechanics to tension, perfection, and randomness, and for predictability and laws to emerge from this randomness. And that in fantasy creation, if we imagine a universe without random energy fluctuations, we wouldn't have chemistry, we wouldn't have DNA, we wouldn't have enzymes, we wouldn't have life. The universe would be cold and sterile. And that actually the best engineers already know this, and they have been relying for years on using randomness intentionally to make many of the tools which we consider essential for modern life, including nuclear power stations, steel, and transformers. And with that, I'm going to stop. Thank you very much for your attention wherever you are, and I'd be very happy to turn to some of the questions that hopefully you've been submitting. Thank you.
Well, thank you very much. I'm still, my video is muted by the host, so you'll see me properly in a minute. While I'm waiting for them to do that, let me say something about myself. Oh, I've come back, great. I didn't introduce myself. I'm Bob White. I'm the director of the Faraday Institute, so it's a great pleasure to welcome all our viewers and listeners today. Thank you for joining us. And at this point, if this was a live lecture, which it sort of is, we'd give a great round of applause to Russell Cowburn. So thank you very much indeed, Russell. I'm sorry that you can't see all the 300 odd people agreeing with that. And I can see lots of comments coming up in the chat to thank you for your lecture. We have had a number of questions. So let me start you with the easy one. This is from Chris Holloway. Is randomness essential to free will?
How long have we got? I think that's really difficult. I don't think it's a simple yes. It comes down to the heart of how do we understand God to work in the world. Randomness is certainly part of that. But it is, as I said at the beginning, it is something theologians have pondered long and hard about how that ties in with his omniscience and omnipotence. And free will is absolutely part of that same basket. So I don't want to say it's as simple as saying free will is what gives saying randomness is what gives the space in an otherwise deterministic world for free will. I think that would be both scientifically and theologically inaccurate. Free will is a complex basket of lots of different things, and I'm sure there's a little bit of randomness sprinkled in there somewhere, but there's an awful lot more as well. Let me give a plug actually for my colleague Dennis Alexander's excellent book, Genes, Determinism, and God, I think it's the third of that triad, where he explores in much more detail essentially free will and all of the other things about genetic determinism. It's a great read.
Thank you, Russell. I'll echo that. Let me ask you a slightly more technical question from Trig. You started by equating randomness and unpredictability at the beginning of your talk, but does that not co-fuse reality and our knowledge of it? So for instance, chaotic structures may be unpredictable, but still deterministic. And you might have the same argument for interpretations of quantum mechanics. So can you give us your thoughts on that?
Yeah, sure.
Please?
Yeah, this is something that I'm currently writing this up as a paper, and this is something we are debating long and hard within the paper. I think chaotic structures are a good example because those appear to be unpredictable, and yet they are strictly deterministic. It's just we don't have enough information to be able to predict them deterministically, and therefore they look random. But strictly speaking, a chaotic structure is not a random one. So there will certainly be some cases where things appear, that I guess we could call them functionally random, where as far as we are concerned, we cannot tell the outcome. And this is I guess the most famous example is the butterfly effect in chaotic weather systems. The thing that stops us from predicting whether the cyclone comes is whether a particular butterfly flapped its wings in the Amazon or not. We don't know that, therefore we can't predict what's going to happen next. So there will be some cases like that, things that are functionally random but are actually deterministic. But then you've got other things like radioactive decay, which are truly random. And it's not just a lack of information on our part. It is, as far as we understand, at its very essence, random. And certainly a Copenhagen interpretation of quantum mechanics would fall into that category as well.
Here's a sort of related thing. You sort of addressed this in your conclusions, but perhaps you could amplify it a bit. Do you think we need a different word to differentiate the order that comes from randomness, to distinguish between that randomness that we associate with purposelessness and the mere throwing of a dice? If you can see the thrust of that. Should we bring a different word into use rather than random?
I think the problem is that quite often that order and purpose, those are emergent properties from the underlying random actions. And so it's not just that we're using the wrong word, it's also a question of which length scale we're looking at. So in evolution, for example, if I look at the reproduction of a single pair of animals and look at their particular child and whether it lives or dies, I can't learn anything really. But if I look at the entire population, I can see how the process of natural selection is guiding that population to become better adapted to its environment. So there you've got both types going on at once. And it's not so much that we're misnaming it, it's just we have to distinguish the emergent, the big scale purpose from the individual action.
Yeah, thank you. Here's actually, this is a question for physicists. Some physicists have been critical of statistics as being a sort of cop-out of not having done enough science. But isn't statistics the best tool we have for dealing with randomness?
It is absolutely, and I'm not sure scientists have been critical of statistics. It's mathematicians, it's pure mathematicians who are the most scathing about statistics, because statistics don't have quite the same axiomatic base that pure maths does. You can't derive statistics quite as strongly as you can some aspects of pure maths. Whereas physicists are notoriously lax with the mathematics, and we do all sorts of horrendous things that pure mathematicians throw their hands up in horror at. So actually physicists and scientists in general are very relaxed about using statistics because it works. It is a great mathematical tool for dealing with messy experimental data. So if it works, we don't complain.
Yes. Today we're talking about origins, a better story about origins. And here's a question about the fall. Now, there will be another talk in British time at 8 p.m. tonight, looking at the biblical view in Genesis of the fall. But this is a question for you then that perhaps you can give your thoughts on. In speaking of the fall, people imagine an original perfection, by which I think the questioner is thinking of very deterministic, no random processes and so on. So they're asking, have you not proved that such original perfection could never have existed in this universe? If that's what the fall was meant to mean.
Yeah, sure. I mean, yes, I understand where that question is coming from. It's something I've thought quite a lot about, as to, and indeed continue to think about, as to how we understand a pre-fall world, as to what exactly is the world described in Genesis 1 and 2, and how does that relate to things like randomness, and indeed to evolution and death. I think there is a chain of logic which says randomness is bad, the pre-fall world was perfect, therefore there can't have been any randomness. But I think that is a false chain. And I think that actually the false part in it is the belief that randomness is bad and doesn't belong in a pre-fall perfection. I mean, with my physics hat on, the creation of the stars, the fact that there is sun, the sun is a hugely random process. It's built on nuclear fusion of tritium and deuterium, randomly fusing and releasing energy. So the moment there is the creation of a star, there are clearly random processes going on. And so I don't think we can say that randomness has no place pre-fall. I think that's just because we believe that randomness is wrong and bad and therefore inappropriate for a pre-fall world.
Yes, thank you. There's a sort of related comment from Peter Skett, who, and I think you've covered it partly already, but you might want to amplify it a bit, which is talking about post-fall events. We often associate randomness with destructive events like earthquakes and volcanism. We generally view these as bad, though some of you who know me know that I'm an earth scientist, so I love volcanoes. That's what I study, volcanoes and earthquakes, and I think they're not all bad. But the questioner asks, we generally view these as bad, yet they are fundamental to how our world works. And how do you deal with this, Russell?
That's exactly it. And I mean, if I'd had time, that would have been another example I would have given, actually, that it's all of the same category, that we have to break this simple association between randomness and badness. That is not right. Just as in the volcano case, we have to break that link between apparently destructive things and badness. It's much more nuanced than that. And just as the universe would be cold and sterile without random energy fluctuations, you know better than I do, Bob, the planet would be sterile and very bad for agriculture if we didn't have volcanoes and things like that. So,
indeed, I would have said exactly that. So, thank you. There's several questions about intelligent design, where intelligent design theory shows that God is a God of order, and yet we've been talking today about God being a God of both order and randomness, if you like. Though I think you'd probably draw a distinction between chaos and disorder, but so how would you address people who talk about intelligent design as being a God of order and evolution maybe not showing that order in the same way?
Sure. I think I would say two things. I mean, firstly, personally speaking, I do not accept the idea of intelligent design. That's not to say that God isn't intelligent, and it's not to say that God isn't a designer, but that particular bundle of ideas that we tend to call intelligent design or ID, I think part of it emerges actually from this uneasiness with randomness. So people talk about, in intelligent design, about special creation, an irreducible complexity. So there are parts of the scientific model of creation that people say is not feasible, and therefore God had to step in and do something special. And I mean, there are so many problems at so many levels, but a lot of it actually comes from the feeling that God needs to overrule the randomness in certain places. And I think part of that does come from this feeling that randomness is not worthy of him, and that a creation where he doesn't overrule the randomness is somehow less intelligently designed. I think so. I want to say, let's turn this round and say God, in his intelligence, like engineers who build nuclear power plants and steel chose to use randomness as one of his key tools for achieving his ends. So I'm still maintaining the fact that God is creator, that this is entirely his creation. Nothing has escaped his control or his will by using random processes. But in his wisdom, he's invoked this wonderful, rich technique of randomness that many of us can only look at and be envious of and try to imitate and use occasionally in our own work when we're able to. God has chosen the best job for the best tool for the job.
Thank you. There's been many questions, so I'm trying to group some of them together so I hope that we're scratching where it itches. There have been a number of questions about suffering, which of course is a very common problem with the evolutionary explanation. It appears to involve a lot of killing and suffering along the way. But one that's perhaps more poignant for humans facing the COVID crisis as we are at the minute is, how can we deal with some of, this person suggests they're unintentional side effects, some of the side effects of randomness, such as cancer?
Mm-hmm. Yeah, I mean, it is absolutely right. That's when I described natural selection, evolution by natural selection as merciful because of its ability to adapt. It is those same random mutations that lead to cancer and genetic disease and all of the other things that that afflict humans. As a Christian, all I can say, God never promised us a pain-free experience. We have no right to expect one, at least this side of heaven. One of the mechanisms that it seems that suffering enters the world is through genetic mutation, which again, randomness has a role to play in. But I don't think that negates the appropriateness of randomness. It would only do so if we believed we had the right to live in a pain-free world, but we don't. And it is, as to quote Dennis again, nature is a package deal. Those same random processes that lead to our ability to survive are the same processes that lead to cancer and genetic disease.
Thank you. Well, thank you, Russell. Our time is up, I'm afraid. We could talk for a long time, but thank you for opening our eyes to something which many of us have not perhaps thought so deeply about, that randomness can be a good thing, a sign of this good creation, and is useful in it, and makes it such a wonderful place to live. So thank you so much for that.